this topic is more of a subject which was crammed into one week. Because I don't think there was a proper justice to this remote sensing aspect of the ML in soil and crop management. So, if you need to know more about this, I request you to follow some proper remote sensing books, or if you are actually doing something in field, then it will be then practical application is always better. Just a minute, I'll be back. 1 minute. Yeah. So we'll uh, go through some of the concepts that were taught today. And for the examples, you can always refer to the slides. I don't like discussing the examples because this is not my prime area of research. So I'm not well versed with these examples that were discussed. So we will be discussing week 5. So week 4, I apologize. I was not able to take it on Sunday, but we conducted the session last Friday. So if you missed that, you can watch the videos in YouTube. So what are the remote sensing aspects in the ML? So let me just write it here, remote sensing aspects. Okay, so in the starting of this, I am audible, right? Can you tell me? Just a minute, I will check. Hello?
Hello.
Oh, fine. Okay, so I'm audible. So what do we need to know first about remote sensing? Remote sensing is done basically. So we have a terrain. Let's talk about the proper remote sensing that is done from the satellites. So we have satellite, we have some terrain. Now we want to know some property of this terrain. So what happens is these objects on the soil, they reflect light that comes to them. Let's say so there is active and passive remote sensing. Then again, that where the light source is, when the light source is sun, then it is passive, and or when the source of radiation is on the satellite itself, then it is active. So that is there. So the reflectance, but the main concept is the reflectance of different type of radiations based on the wavelength depends on the property of these uh, depends on the property of the things that we want to know. So let's say we all know why anything looks of any color, right? The plants, why the leaves look green color, because they reflect green light while absorbing most of the other radiations, right? In the visible range, they reflect the infrared and all also. So that is another thing. But talking in the visible range, they look green because they reflect green. So something like that is there for all the radiations in the electromagnetic spectrum and all the objects that exist. So we use cleverly these reflectance. So let's consider this that there is a sun as a source, and light ray comes, it hits this object, and then it reflects something. So from the space also, if you know, we have some nice Google images from the space. So similarly we can have different kind of images of the space. So let's say we take a picture of this whole terrain from this, and based on the sensor that is installed in this satellite, we can install sensor that takes image for a certain range of wavelength, like let's say in the visible range 400 to 700 nanometer, then in the infrared, near infrared uh, greater than 700 and less than, I feel, less than in less than 2000 or 1500, something like that. Less than 2000, yeah. So these are the range. So we can have sensors, different sensors that actually are designed based on the diodes that are in them to activate or to ignore, to give a reading when a wavelength or an energy or a radiation of certain within a certain range hits them. So that gives us a picture, that gives us a raster. So because images, if you know, are made up of pixels. So what here you see my screen also, the screen that you are able to see in your monitor, they are all made up of pixels. So likewise, the photos that we get are all of pixels with small boxes. In normal images, we have different concentrations of red, green, and blue lights, and that gives us these all different kind of colors. Whereas in the remote sensing or the spectral matrices, we can have band 1, which belongs to some wavelength range, band 2, which belongs to some other wavelength range, and so on. So now that we know what is the output of remote sensing, that is just a spectral matrix, a 3D spectral matrix, so to say, because what we will have is, this is, let's say, the photo of the terrain with lot of pixels, and then we'll have these the photo for different bands. So it's like stacked on top of each other. So we get this kind of matrix. Now, when we have panchromatic band, so when we have panchromatic band, that means usually that we have only black and white. So we have only two bands. Sorry, we have only two variations, either black or either white. And it is a single band. So let's say if I have, let me just shift it down. Let's say if I have my wavelength, where in between I have our visible light. So let's say this is visible light, and this is the wavelength which is increasing in. Sorry, if it is increasing here, then I should put it like this. Yeah. So in this, on the right side, when we go, it is increasing. Then when we talk about panchromatic band, we will have one single band which is wide. So let's say it is covering your visible range also, and some of the infrared range also, right? Some of the UV range also. So it is a wider band, but a single band, and usually it is black and white. So when we have only one band, that means a lot of information is getting clubbed together. So you won't be able to distinguish between a leaf and let's say building, because building may be of gray color and a leaf of green color. So but this the sensors that are installed in these satellites or any or the diode that is there for sensing these lights will activate for both of these things. So we will not be able to get much finer details using this panchromatic band. So that's why we have multispectral band. Now, what is multispectral? It is not the best, but it is the next best thing. That is, if in among on the wavelength line, on the wavelength line, if you see, we will have multiple little less wider bands. So this is one, this is one, this is one, and let's say that we give one band for visible. I'm just talking in hypothetical terms to explain to you. So this is multispectral. That here we had one only very big wide. Now here we have, let me write it here also, only one wide band, right? Multiple medium range band. Usually 3 to 15, when you have number of bands from 3 to 15, we can call them multiple. So we can use them when we have, let's say, one we want to do for soil and some other things. So soil, as you will see in the would have seen in the week's lecture, that soil is good when we are going for a mid infrared range. So maybe if we distinguish the visible from that, we can use this multispectral. And even better than that is hyperspectral. Nowadays this is being used. So in this case we have hundreds of narrow bands. So here we had like 3 to 15 medium bands. In this case of hyperspectral band, we have hundreds of narrow bands. So we have small bands, and we have numerous number of these bands. So effectively, if you see, we are covering the whole wavelength, and at the same time a lot of the details are also covered. So let's say this was the visible, so I am actually separating visible also into two. So if some things are blue or some things are red, we'll be able to distinguish between them also. And the best is ultraspectral. This actually is not very common because it needs a lot of data, because there are thousands of narrow bands when you talk about ultraspectral, right? Our focus will be on will not be on these bands. Will be after we get these bands, how we do all the other kind of analysis. Our focus will be on that. And we have, when we what is the output from all these spectroscopy or the remote sensing is the image cube, as I discussed, as I showed earlier, is the image cube. Basically just the image, how the image looks like when you only capture the light coming from within lambda 1 to lambda 2 wavelength range. So let's say this is that particular set, and then how the image looks like when you capture the light coming from the range lambda 3 to lambda 4 and so on. We have very big, we have n number of images, and this is the image cube that we get. Now where else we have seen this image cube? As I told earlier, the images that you see, the screen that you are seeing at this moment is an image, not cube but cuboid. How? Because let's say this is your screen. So your screen actually at this moment, at this present moment is showing you three matrices, or three matrices of red, blue, and green. lights. So for one matrix of will be containing the red light. So as I draw this red color here, and if you are able to separate that matrix somehow, you will see that particular matrix at this moment will have will look something like this. So this will be your screen. Some places here it will be more intensity for red, and then here it will be the highest intensity for red. And other places there will be some noises because all the colors are made up of RGB, but the maximum intensity will be at these points. And in the same way the other colors, where like for the white you will have in high intensity for all these things. For RGB everyone will be high, then we get the white. So basically maybe then in that case you will have the low intensity for blue and green at this place. So you can visualize that image cube if you think like this. No need to go for wavelength, just you visualize based on the image that I'm seeing. Okay, so as I said, hyperspectral bands are the talk these days. So let's see some of the sensors that are used in this hyperspectral sensors. Okay, so what are the things that the sensors are going to cover? They are going to get the spectral information. What is spectral information? It is that which wavelength is getting reflected. Then they have to measure the intensity. Now, why do we need intensity? See, as I told that all the colors actually have the red, blue, and green within them, but different intensity of red, blue, green decides that whether the color is going to look like white or black, right, or yellow or red. So for that we need the intensity information also, and we have image. Now, when we know all these things, which area or which particular region does these things actually correspond to? For that, we need a spatial information. So for that, we need some image also. So let me write here spatial information. So the things that provide us these informations are spectrometer, then radiometer, and then we have image. So image sensor. When we combine these three sensors into one, it is called imaging spectroradiometer, which is usually what is present on the satellites. But there is something more. There is one more important group which doesn't involve the photography or the spatial awareness, spatial information. That is spectroradiometer. It only gives us the information about spectrometer, like the spectral information and the intensity. So why would we need this? Why would we need spectroradiometer, which only tells us about the intensity of the wavelength and actually which wavelength we are talking about? Because most of the time, or always I should say, these spectroradiometers are used on the ground. And in this situation, we already know which area or which position we are looking the information for. We want the information. So on the ground test, these things, this spectroradiometer is used, and we are going to talk about this spectroradiometer only in this session. We are not going to the remote sensing aspect of that. Just a brief summary of remote sensing I gave, but in the in our discussions will be limited to the spectroradiometer, which is used for the soil spectroscopy. We use Now we know that we use spectroradiometer mostly for the soil spectroscopy, like as a ground base. We also use the other techniques of we also use the imaging spectroradiometer from the satellite, but as a ground base we use the spectroradiometer. Now what is soil spectroscopy? It is the study of the spectral signature of different components in the soil, the inorganic components, the organic components, the moisture. So we need to identify, the study of spectral signature of soil. So what information do we get from this spectral signature? So as I said, every element has its own unique way of reflecting, absorbing, or transmitting a radiation. So spectral signature relates to soil characteristics such as organic and its mineral components. It is related to the soil characteristics, organic content, mineral content. You can also say moisture content. Let's call that water content, right? And why do we prefer this? See, when if we know how much organic content, moisture content, and let's say if we have a way to identify, or even better, like if we have a lot of small size particles in the soil, then it will have a different kind of reflectance. Then if we have lot of big size, so based on that, if we have a little finer, or we have a better instrument, we can actually do the classification of soil also. So we can avoid a tedious lab process, right? So if in the lab we have to do hydrometer analysis, we have to do wet sieve analysis, then dry sieve analysis to perform the soil classification, and then we have to do that multiple number of times to actually be correct about the soil properties. So if this soil spectroscopy works, then it makes our process much more fast and also non-destructive. Now why do I say non-destructive? Is because when we want to perform tests on soil, we actually take the soil out of the location and then mix it with water and other chemicals, right? So it makes that soil, now the soil is not usable. Now it may be usable for further tests and all, but it is not usable because it is not having the same composition as before when we took it from the site, so it is disturbed, right? So this process is also non-destructive. That might not incite much benefit in your mind at the moment, but if you have some experience in the field, in geotech labs, then you will be able to relate to it. Okay, now also it was discussed that visible to near infrared range actually overlaps a lot of information when it comes to soil spectroscopy. So the best range, or the best way to do this classification of soil, is when we use middle infrared range. So middle infrared range is better for soil spectroscopy. Okay, now how do we perform actually this? How do we use this remote sensing information or all the matrices that we have? So there are steps or the points to remember that was mentioned. So let me just recite them back. So what are the points? So what do we need to do when we want to get this? First of all, we have to use, let me call them as points only because they are not exactly steps. Yeah. First is we have to use middle infrared range for the soil spectroscopy. We can also use, as it was told in class, that not always this process is followed. But then, in that case, if we are using some other radiation or other wave band, then in that case we have to do a lot of filtering of the data, right? So that's why it is preferred to use this because it gives much higher accuracy. Okay, so yeah, okay. This is first. The second is now we have to extract the information. What we get from that, we already discussed that from our remote sensing or spectroscopy, we are just going to get cuboidal or cubical matrices. So how do we map it? To map this data, we have to make a function. We have to make a function that takes input of the readings in these places, in these matrix places, and then relates it to the actual value. Let's for instance, let's say that I want to know the organic content of the soil. Now I have this matrix. How do we get that organic content? Even if I don't have this matrix, let's say I have done only, I did, I used a ground based sensor, that is ground based sensor. So I only have values. Let's say I have a value of how much the wavelength in the middle infrared range was, how much intensity of reflectance was observed in this. Let's say I on top of that I have uh, so it was from, let's say, in the middle infrared range also I use hyperspectroscopy. So I have lots of band also in the middle infrared range. So this is from lambda 1 to lambda 2, lambda 3, or lambda 2 to lambda 3, and so on. Let's say I have five values of intensity from, or four values from middle infrared range. Now what we do is we fit a model, whether it be PCR model, whether it be PLSR model, which is also very useful, or it can be random forest when you are just doing a soil classification, or it can be a neural network, right? So you can fit anything feasible that you want to fit based on these things, and then you can get, or you can also fit logistic regression. Yeah, you can also fit simple logistic regression. The accuracy will be lower, but you can fit the models and get an output. So let's say your output was whether it is, it's, if it's a classification, like either it is a highly organic soil, it is silt, it is clay, what is your classification, then you can give it 0, 1, 2. Or if it was actually about the moisture content 15, then instead of using a sigmoidal function for classification, you can use a ReLU function for moisture content. These are all not things to worry about, that may come in the future sessions and we'll discuss. But just I'm saying that we can use these data to do either classification or regression. So for that, we need a transfer function. Transfer function is nothing but this model only. So if we have these four values, what basically all these neural networks, logistic regression, PLSR, PCA, all these things give you is that you multiply some value with this first one, Let's say with this first intensity you multiply A, second intensity you multiply B, and all those things, and then you get the value which is actually equal to your moisture content or organic content, right? So this these are all the transfer function that is being discussed in this. No, it was discussed in the points to remember. So we get that transfer function based on our model calibration or valid, yeah, model calibration, and we use that. We can use that transfer function after we obtain a good high accuracy transfer function. We can use that for making further predictions, further much faster, you know, predictions. So get a transfer function based on the data obtained earlier, and then we can use the transfer function. Okay, now one more thing that is important is these things actually are site specific, right? So we need to do this process for all the sites separately, meaning that you cannot use something that you did on Chennai. You cannot use the same parameter or transfer function which you used on Chennai to do it in Punjab, right? So you need to perform this kind of analysis in the soils that are found in Punjab or some other state also. And that to do this model validation and calibration, there is something called spectral library that is made for different sites. So your site may have the spectral library or it may not have. So what is this spectral library? So simply speaking, it is nothing but the values of the reflectance, the intensity of the reflectance that are obtained from different sensors and corresponding labels of that soil. So if we have a sample and let's say we have wavelength bands in that and we get some intensities, now what we do, we perform the laboratory experiments on these samples and we get to know that whether this is organic, uh, let's say, to avoid any confusion, let's say whether it is clay, silt, clayey loam, silty loam, or all these things. We make a directory of all the reflectance intensities and their corresponding labels. So this is what is your spectral library is called. Now, how do you make this spectral library? One thing you can do is, you know, that in a particular region, that is so I'm talking about the legacy soil sample right now. So you know, for a particular region you have certain type of soil. So you know, for a certain region, this is your map of the home. Let's say in your backyard you have actually you have performed some tests and you know that this is a clay soil, clay loam. So what do you do then? You perform spectral analysis on this soil sample, but not just once. You perform it multiple number of times, and you then plot it in a bar plot or a scatter plot. Let's say now we had three, right? So we can easily represent it. So you did some laboratory experiment. You found out in your backyard you have clay loam, right? And now you did multiple spectroscopy, soil spectroscopy tests on that, and then you plotted the intensity of the three wave bands. What will happen in this case is, if you have a homogeneous soil, or if you only have clay loam soil or one kind of soil in your backyard, you will see that all the points will actually lie close to each other. But let's say I outsmarted you, and on half of your soil of landfill, or not landfill, half of your backyard, I came and dumped some sand in it. What will happen if you come to do the analysis in this region? You will get some points that are not not close to the normal average that you want to see. So in that case, what you have to do is, when you are talking about this legacy soil sample, you have to redo this scanning. So if outlier is observed, this is what I am describing the outliers as. If outlier is there, outlier is present, then either you redo the scanning, and if still you see this outlier, you will see, because I have put clay in your sand in your backyard, then you either redefine this as a new soil sample, you perform the test and then give this another name. So like make a new entry in your spectral library, make a new entry, or you go and test your instrument that you are using for soil spectroscopy. So maybe it is that I was not putting sand in your backyard, I was actually putting clay, but your sensor is saying that it is sand. In that case, your sensor is faulty, so you need to replace that sensor. So these are the steps that you can use to make your spectral library. So the same thing you will do if you don't have the legacy soil sample. You go to different sites and scan new soils. But then again, you do this kind of check of outliers. Okay. So let's say once you have this spectral library, you did your soil spectroscopy tests and you obtained matrix, let's say matrix of 100 soil samples across five wavelength bands, and then you perform laboratory tests also. So 100 cross 1, let's say it is organic content, so 10%, 5%, 0%, and all those things you perform. Now using this spectral library, you can actually uh, give predict about the organic content of soil that exists, that is there in in that particular site locality, in different location. So this is your spectral library, but you have to be careful with one thing. Library. So here you observe first, one check we are still left to do is, this is one feature, this is one feature, this is another. So these are all five features. When you have five bands of wavelength, then that means these all bands are features. Now they will have a minimum value and a maximum value. So let's say it is x1, x2, x3, x4, x5. They will have some bound, lower bound and upper bound, lower bound, upper bound. So when you are going to use this spectral library to perform any kind of classification or regression, then you do the spectroscopy test on the new sample. You do the test, you get the five readings, but your answer or your prediction will only be considered good enough if, or reliable if, all these five readings that you have obtained are within the range of these five readings that you used your model with. Because if you don't have the new spectral readings within this range, then that means your model is going into uncharted territory. It is going to do some kind of extrapolation, and extrapolation is always going to give some bias or unpredictable result. So only when your I'll just let me just try erase this and I'll write it here. So when we are talking about using the spectral library, then in that case, check if the spectral data, check if spectral data, the new data that you obtain, is in the domain of the library? If it is, then predict. If not, perform laboratory test and add it to your library, thereby making your spectral library much more robust. Okay. So one question that must occur was why we are actually doing this ground-based studies when we have the image spectroradiometers, when we have the satellite data, why we are actually doing this ground-based studies. See, when we have satellite data, let me give you an example. Let me give you an example. Let's say you only had in the satellite, like an image, you had RGB, right? Like in image, you have RGB sensors in your satellite. Now it is going to give you which part of this field. Let's say this is a field you took an image of. Which part of this field is actually a farmland with more green, and then some other homes, right? But one more thing you observed in your data was you got a patch like this, a green patch. Whereas your farmland, you knew that field, and you knew that there was no farmland or no tree on this side of the field. So how do we actually distinguish it? So I am just giving a hypothetical example to explain to you why we need these spectroradiometers. So how do we fix it? So when we go to the field, right? When we go to the field, we observe that this is actually a home, and this person has painted his home green. Now, since I removed already the NIR and all the other wave bands, you have only RGB. You will actually not be able to distinguish between these two readings when you look at only the wavelengths. Maybe if you have an image, you will be able to distinguish that. But if you are only having these things, only the green data, you may not be able to distinguish that. So that's why we need some ground proof. That's not the only reason we need ground proofing. One more and much more significant reason is we need to calibrate our satellite data also. So let's say you got the satellite data, and now you want to know whether this data, this particular at this point, my satellite data corresponds to what, or whether my satellite data is even correct or not. Then to know the ground truth values, these spectroradiometers are important. And also sometimes there may be clouds, and you may not be able to see what is actually on the part of the field, you may not be able to see. Let's say there is a cloud here and you're not able to see, so we cannot just remove that. So we use some kind of ground truth values, ground truth values, and we extrapolate and get using some mathematical functions, we get our new mesh. We remove the cloud cover. So this is why these spectroradiometers are important. So we can go to the field and perform the actual tests on the soil where we don't have. So it sets a reference data for the satellite, and also the ground truth value for the thing, for our satellite data. So why we need this spectroradiometer? Because it gives us reference and ground truth values, and also it is this is not a reason, but spectroradiometer studies are pixel based, right? So what do you mean when I say pixel based? That means in your image in the remote sensing, you have one reading for this pixel, right? You have one reading for all the bands for this pixel. So similarly, you go to this particular area in the ground and you perform the tests in maybe different places, because coming to the ground, if you are familiar with remote sensing, you will know that your grid actually is a big area. So Google Image gives us point 0.2 to point 0.2, I think it is meter resolution. Still, it is 20 centimeter by 20 centimeter. So, and some other satellites are even give 2 kilometer by 2 kilometer resolution, right? So their one pixel actually is 2 kilometer by 2 kilometer. So when you have all this kind of study, then but from the remote sensing. So you do the ground-based tests in some of these regions. In the 2 kilometer by 2 kilometer, you do it in two, three places, and then you give the reading to your satellite. So it's a single pixel-based study. It is not like a whole area coverage. It does the tests one time at a time, one point at a time. Let me write here point-based also. Okay, so that's about why we need spectroradiometer. Now there were some discussion about the sensors and some literature, how they have been used in the in the research. You can go through all those things in the PPT or in the lecture yourself. We'll not go in that because I'm not qualified to talk about those things. As I told earlier, it's not primary research, my primary area of interest. What we can do is I can summarize the important things that can be asked in the question in terms of in the exam in terms of two questions. So if you want, you are feel free to answer these two questions. So question number one is, what is FWHM? And I'm not talking about the full form. The full form will be full width half maximum, like what it signifies. So I'll give you options. Let's say you have two options. First is sampling interval, and second is spectral resolution. So if you want to try, you can put you can put message in the chat group, either A or B. I will, yeah. So and others, if you want to try, you can pause the video. So the answer for this, A. Okay, so that is not correct actually. Full width half maximum actually describes the spectral resolution. So it is B. So but nice. Thank you for trying it at least, because most of the time people don't try. And when once you get something wrong, one thing I can say that it is very less likely that you will get it wrong again. So it is good to make mistakes before they start making changes to our grades. Okay, now if we have a feature in the soil, for a soil feature to be detected by this spectroscopy, the feature must be space, and then the spectral resolution, or let me just say, so feature must be A smaller or B larger. Yeah, so if we want to detect some feature in the soil. Let's remove the soil. If you want to detect a feature, for a feature to be detected, that feature has to be smaller or larger than the spectral resolution. What do you think? I'll explain it to you with an example. So it has to be larger. Yes, correct. It has to be larger than the spectral resolution. So let me give an example if anyone was not able to identify that. Let's say you have a nice raster, and when I say resolution, I mean that the area of this thing, the area of one pixel is the resolution. That's what I am talking about. Now, this let's say you have a tree and you want the tree to be detected. You want to detect that feature. If that feature, that tree, is smaller than one cell, it will not be able to detect the tree. It will just get some reading. It will average out the tree and the soil nearby. Whereas if you have the tree bigger than this pixel, let's say it takes 4 5 pixels, then what you will observe is that you will have, oh, sorry, you will have green in this pixel, green in this pixel. Now you can easily identify that actually there was something green here which might be a tree. So a feature, when it has to be, when we want to detect it, when it is detected in a spectroscopy, then that feature is like larger than the spectral resolution. This is just an example to explain. This question was to explain this question. You This is not the case in like not exactly the case in terms of soil, but it makes it easier to explain this way. Okay, now how what type of spectrometers we have? Let's talk about some of the spectrometers. We'll have predominantly two type of spectrometers. We'll have multiple type of spectrometers, but based on the process of inclusion of the ambient light at this time, we have two type of spectrometers. One is pre-dispersive spectrometer, another is post-dispersive spectrometer. So pre-dispersive and post-dispersive. Now, if you have watched the video, you will know that pre-dispersive is better. But why is it better? All these, both the sensors are actually taking in light that is reflected from the object that they are going to scan. So, what actually is better in this post-dispersive? In this post-dispersive, the reflectance, or maybe the we should say the signal, constitutes the most of the size of data. Whereas in this pre-dispersive, ambient stray light also, ambient stray light, or you can just say ambient light, is high in proportion. So the information that we want, actually, that is the whole goal of this spectroscopy, is less. Hmm, Literally more noise and less noise. So what does this post-dispersive spectroscopy or spectrometer do that avoids this? So first of all, they also take the ambient stray light, but they take the ambient stray light through a different sensor. Post dispersive instrument. and that too they take only that wavelength which is within the wave band which they are observing. Only that wavelength that is being measured. Okay. And in this case, all the ambient stray lights are allowed along with the data that we want to measure. So we'll not go into technicalities how it is going to avoid all those things because that is not very important. Then there were this we discussed some of the components like in the session it was discussed about different components, right? Just one thing to remember that can come as a question is which kind of which yeah, let me put it as a question itself. Which field of view is better for large coverage? Is give it as a yeah space. Is it a smaller field of view or B larger field of view? It doesn't even constitute as a question. It should be so simple to answer. So when we talk about field of view of a spectrometer, it's just like if you have a sensor here and you have some lens here. So this is the area it is going to cover in circle. So if this is the front view, top view, if you see, it will be like this. There are some formulas to do this calculation of this area. So I am asking if we want to cover more area, which field of view is better? A bigger field of view or a smaller field of view? The answer is pretty straightforward. You have to have a larger field of view to be able to cover large area. Okay. So I think it was by mistake, but please make sure that your mic is turned off. Yeah, so after all these things, we have collected our data, we have done the, we have used our post dispersive spectrometer for collecting our data. Still, we have a lot of things to do before we can use this uh, spectral matrix for our analysis. They are called pre-processing processes. Pre-processing processes. Yeah, that's a nice way to put it. So, what is the need of these pre-processing steps? Let's call them need of pre-processing. Fairly obvious. We want to reduce noise, reduce the scattering noise, and second is we want to remove any error if there are. We cannot reduce the noise but remove the noise, but we can definitely reduce it. So what are the some few of the important steps that were discussed that we can take to do this pre-processing or make our results more accurate? One among them is very important, is to change the reflectance matrix into absorbance matrix. If you consider transmittance as 0, then absorbance is nothing but 1 minus reflectance, but different things will have different properties. So uh, it may depend on the study or field area where you are doing this analysis. Now, spectral trimming. Second is spectral trimming. Let's say we had the hyperspectral sensor, and we have like we have the readings at very fine narrow bands, and we have numerous number of readings, but we want to do the analysis only for soil. In that case, we don't want all these wavelengths. We don't want most of the visible region, right? And then we don't want ultraviolet, we don't want the high infrareds. So what do? We delete all the bands or all the information that belongs to this external uh, wave bands. So to put it in one line, it is cut off. We cut off the data of wavelengths that contains no useful information for us. Cut off the data for wavelengths that contain no useful information for us. Typically, 500 to 2450 nanometer is kept because it gives higher signal to noise ratio. But it will change if you have different things to scan. Now we have moving window average. So this is, as we can see in the name itself, it is an averaging process. Why do we need this kind of averaging process? It is to reduce the noise. One of the major drawback of this thing is that it also reduces the information that you have in that data. But if you are able to manage the parameters of this correctly, you will not lose that much, because the basic principle behind this moving window average is that the information about any wavelength information about any wavelength is given as average of its neighbor. So if you have a big enough, very big window in this, let's say this is some kind of absorbance and the wavelength, and you have a very big window, then you can see that this will become one straight line, and it will not be a very good kind of averaging. So a small, or maybe let's say it was the data was not very this clear. The data was something like this, right? So if you had small averaging, then maybe you will get a little better approximation. But if you have very large window, big averaging, then maybe you will end up with only these things, right? So which will not be good. So managing this window width or the moving window is important. Drawback is it reduces the information also along with noise. Mr. Okay, yeah, thank you. Okay, so what is the fourth method? I don't know how to pronounce this. I will just say SG, or maybe I'll write it. I don't want to say the name wrongly. SG filtering. What do we do in this case? So let's say if similarly like this, the above case, we had wavelength and then absorbance, and we had this kind of data. Then we try to fit a polynomial in this data based on the window size. Let's say I again, here also we have window size. Let's say I have this window size. Now what I will do is I'll try to fit a k order polynomial for the data within this window. So maybe in this window I get this kind of polynomial. In this window I get this kind of polynomial. Here I get this kind. So like this we will get a smooth trend, smoothness in our data without losing much of the information as compared to the moving window average. So what do we do here? We fit a polynomial of order k to get the smooth value for each wavelength. It also has the window size. So higher window size, information loss is uh, when you have higher window size, then you'll have more information loss, but more smoothness also. But you have more number of windows, it will be better. Okay, now what do we have? Some more techniques are there. These are all techniques to remove the the randomness in the data, the scattering problem in the data. When you have the soil spectroscopy, and you have as you know that soil grains are not of the same size, so in that case there can be a problem of scattering or deviation or amplification problem in your spectroscopy data when you are doing further scaling and analysis. So to remove those problems, we had two special kind of pre-processing techniques, that are SNV and MSC, standard normal variate, and we have multiple scattering correction. Multiple scatter correction, sorry. Standard normal variate is nothing but making your data so that its mean nu is 0 and standard deviation is 1. How we can do that? You can do that by xi is equal to xi minus nu divided by standard deviation. You have your data, you calculate the mean, you calculate the standard deviation, then do this operation for all the values of x or the absorbance that you have, and you get the new absorbance value based on this formula. So that's how you will actually get a standard normal variate data, which will have less values. What multiple scatter correction does is that it tries to align all the spectral trends or all the spectral data with one reference using the least square method, and in doing so it tries to makes the baseline same, and removes the error that will be introduced when uh, further amplification or other operations are done. The here we'll not see, we'll not talk about the method. We'll just write it. What basically it does is each spectrum is fitted to the reference spectrum using the least square method, linear method, but the parameters of that method are obtained using the least square method. Now it removes, in doing so, it removes the amplification and baseline error. One last one last thing that I am also not very clear about how this works actually is detrending, but it's not also not very important. It's spectral preprocessing and detrending. It tries to remove the mean. Other than I, other than subtracting the mean, I could not see any physical difference between the two data. We'll just write it as it removes the mean from the spectra, removes the mean or trend. Then again, these methods, these are all just, unless until you use them, they are all just like chemistry. You have to mug them up. So not very interesting topic to discuss actually. Yeah, and then there was CR method that I'm not going to discuss here because it is very weird and difficult and not also very important. We have more interesting topic to discuss than that. That is derivative spectroscopy. Why do we need this derivative spectroscopy? What is the importance of that? Maybe we'll try to understand this a little better using some graphs. Okay, so let's say you had this point, this plot where x-axis is again wavelength and y-axis is reflectance or absorbance or any other value that you are sensor reading, let's say, and you have two wavebands or two different wavebands that you want to combine, two different readings that you want to combine. Now in this case what happens is, if you have something like this, if you have seen the PPT, you will understand that you have two different kinds of readings here in this way. Let's say you got these two readings. You don't want to combine them actually. You want to use them to train your data. You have this, you got in first time you got this, and the second time you got this variation. Now your normal model will have difficulty in distinguishing these two trends because they have same wavelength and amplitude also is not much difference, not much different. But your this trend, it is actually not able to capture the change in curvature. It is not able to capture very clearly. It is not able to capture. So that, and the what actually governs the change in curvature? The derivatives. So that's why we use this derivative spectroscopy, where we perform the derivatives of the readings of your sensor with the wavelength, and then use them as an input of to train our linear regression or PLSR models. So how the derivative is computed, that is not the part of this syllabus right now, but just know that derivative is computed because it gives us more information about the data. Derivative is computed from the raw data. And when derivative is computed, see, we usually don't have the smooth curves. So derivative is computed after we do the trimming and the smoothing. Okay, let me don't repeat it. After initial smoothing and trimming. One more thing, just as a note or a true false question, if you are using the SG method that we discussed, where we are fitting the trend line of kth order, polynomial of kth order, in that case, you can perform the derivative along with when you are doing this smoothing. Okay, so we'll not mention it here, but usually it is done after doing the smoothing and trimming, because you can do that along the smoothing, because once one curve is done you can perform the derivative of that curve. So it's not that important if you are doing the smoothing first and then you are performing the derivative. You can actually do it all together in case of SG method. Okay, now let's see what actually we get. So here you see how actually it will be different. Let's say if you have this curve and you have this curve. Now I will pose a question of what will be, how its derivative will look like. A or B, you have to answer. Its derivative will look like this or this. Don't go for the curvature. Just look at the peaks and tell me. The derivative of this particular function will look like this or this. A or B.
A, sir.
Okay. So A. Uh, what is derivative is the rate of change. So we see that the rate of change of the value here in this case is positive, right? And then after it goes to the peak where the rate of change is zero, it becomes negative. So A will not be correct, because here the rate of change, the derivative is decreasing. Going negative means the value is the function value, actual function value is decreasing, whereas it is increasing. So the correct answer would be B. Okay, now let's give this a shot. So here,
Hello, sir.
yeah,
Sir, in B, there is also increase at the last moment increasing the value of B. मतलब ग्राफ की वैल्यू इंक्रीज हो रही है बी में.
in B the value is increasing. Yeah, so see, okay, maybe
Yes, sir. The in the B firstly the value is increasing of then decreasing then increasing. But as the above diagram shows that the firstly increasing and then decreasing. And how the answer is B.
okay, maybe I also did some mistake. Let me think about it. So we have, let me draw the correct itself then. We have an increasing, so we have positive. It starts from zero. It starts from zero, from a constant value. That means here it is zero. There is no change in derivative. There no change in the value, so derivative is zero. Then it starts to increase. Derivative becomes positive, and then the increase starts to decrease here, so it becomes zero, and then the value decreases, and the rate of decrease, the value of decreasing is becoming zero, like this. Yeah, so this one will be correct, right? Will it not be correct?
Okay, sir. As
See,
you say.
whether the value is decreasing is only governed by whether this plot is positive or negative. We don't care about whether this plot is more positive or more negative. See,
Yes. Okay, okay.
here the value,
Yes, sir. Okay.
you understood? So
Yes,
I'll,
sir.
yeah, okay. So let me just, for the other people, let me just say it once more that here the rate of decrease is more, so the value is more negative. Here the rate of decrease is less, so the value is less negative. And then when it comes to here, the rate of decrease or increase becomes zero, so the derivative also becomes zero. Yes, so this is how we try to make this. Okay, now let's look at this other plot to make it more clear. Hmm. Now let me try to make some example for this. What should be the possible solution? So we have this, or we have, so which one will be the, let me just check once more. Okay, so yeah, I'm also getting confused now, so let me just put it like this. Which one will be now? You might be able to guess now itself. So which one is the answer now? A or B?
I think B, sir.
Yeah, I also think that, but let me just confirm it. So we have increasing from zero, it is increasing, then increase starts to decrease and becomes zero. Then it is decreasing, but the decrease starts to stop when it becomes a plateau here, so it becomes zero here, and then starts to increase, and the increase goes to zero on this plateau, and then it decreases and then comes back to here. Yeah, okay, so this is B. Yeah, I was right, but I thought I made some mistake. So yeah, so see now our if we had used only this data, only this type of readings in our MPLS or other machine learning or curve fitting methods to predict the parameters or predict the reading of the soil, then we'll not have much difference between them. Whereas if we do the derivative spectroscopy and we perform the derivatives of these signals or the readings that we have, then we can easily distinguish between these two. So that's why we need this derivative spectroscopy. Now I have a question, that is, which of the following state, I'll write few statements here. Which of the following statement is false? You have to tell me. So it will, in one paragraph, we'll cover what are the advantages of derivative spectroscopy. Select false. A, derivative spectroscopy. So I'll write 5 lines and then you tell me which one is wrong. Separates two spectra of similar, can be used to separate two spectra of similar delta lambda mix, and it suppresses broader bands. We can use it for noise filtration, then provides lesser peak than the lesser number of peaks. Then E, that is increases signal to noise ratio. So now you tell me which of these statement is false. Okay. So if you have gone through the presentation, you will see that I have only added one more point that is false, whereas all the points are correct. And that point is based on just what we have seen above. So the wrong statement is this: provides lesser peak than the raw data. This is the raw data with only one peak, and this is the uh, data with derivative, and it has two peaks. This is the raw data with two peaks, and this is the raw data with 1, 2, 3, 4 peaks. So it provides more peak than the raw data, and which is good. When you have more peaks, then you have more extremes, and you can easily train your model when you have more information. So all these things are correct. You can go check the PPT if you have not for these. It is able to. So now we are able to easily, with this we are able to easily cover this differential derivative spectroscopy. Okay, the last topic for today's discussion is the external parameter orthogonalization, EPO. So, as it was discussed in the PPT, that when you are performing this soil classification or spectroscopy, when you are performing, then we use middle infrared range because it provides more information. There is no overlap of information, unlike visible and near infrared. But infrared is absorbed by water. So if the soil has water, it is going to absorb the infrared radiation, and it is going to give us false results. Okay, so to do that, they used the power of mathematics to do some operations and try to separate the effect of the water, of the moisture in the soil, from the actual soil. So we have EPO, that is, sorry, external parameter orthogonalization. What is the spelling? Yeah. Which is used to remove the soil moisture content effect on the spectral matrix. Okay, so When we perform this spectroscopy, not visible in screen. Can everyone else see the screen? Is my screen visible for you?
Yes, sir. Your screen is visible.
Okay. So Prachi, maybe you can check the internet connection. Yeah. So as I was saying, that yeah, we want to remove or reduce the effect of soil moisture on our spectral matrix. That's why we have performed this EPO, external parameter orthogonal evaluation. We actually basically similar to PCA that we discussed earlier in the earlier week. It was principal component analysis. We try to orthogonalize the component of soil and moisture in such a way that they are independent of each other. So that's what we theoretically want to do. And to do that, let's say we perform the spectroscopy on the soil and we get a matrix that is the spectral matrix X. Now this spectral matrix will have a component of soil that we want, and it will have a component of from the moisture, and then it will have some noise. So this is the moisture, this is the important value that we want, and this is the noise. Rather than important, let me just write soil. Now xp xq, these are not uh, one entity, it is x into p. So this p is a matrix and q is a matrix, and r, we can understand that it's a matrix. So how do we separate this? To separate this, we first need to perform the spectral analysis on the dry soil. So we dry the soil in an oven, and then we take it out and we perform the spectral analysis again. In that case, and then when we do that, we take a difference between the spectral matrix of the dry soil and the moist soil, and then we call that the new matrix that we get after that as D. So let's say we had X, that is wet, minus X, that is dry. So this new matrix that we get after subtracting this, taking a difference of the spectral matrix from wet soil or moist soil and dry soil, we call that D, difference matrix. And we can get the Q matrix that is actually governing the effect of moisture content of the spectral matrix. We can get this Q when we perform singular value decomposition of matrix D. One thing to note is this singular value decomposition is nothing but when we divide this matrix into three matrices, that is a diagonal matrix in the middle and one matrix on the left side and one on the another. So when we do this, we can get the value of Q. I just wanted to tell what is this because it can be a little intimidating. Now how we do that, that is again out of this out of the content, so we'll not go into that detail, otherwise it is another rabbit hole. We have to do how we have to do, what parameters, what are all these things we need. Now when you get the Q from this, you can get P, that is the contribution of dry soil or only the soil, as I minus Q, where I is the identity matrix. So as I said, this is similar to PCA. So we can do the same thing that is this EPA will do by performing the PCA on D transpose D. that is the multiplication of the transpose of the difference matrix and the difference matrix. If we perform the PC on that, we can and we get the eigenvectors, we can do the same thing as we as the EPO has done or will do on this spectral matrix, and we can orthogonalize the component of soil and moisture so that it doesn't the moisture doesn't affect the soil influence on the spectral matrix. Yeah, and then there was something about the plant. So just one point I want to share, that I think probably it is yeah, it was in your quiz also maybe, that since plants absorb the red light and blue light, they have the lowest uh, this lowest intensity when it comes to the reflectance among the other soil and other things, because red light is has more energy, right? So if it absorbs red light and blue light and it only emits the green light, which is having low energy, so it will have less intensity compared to these two. Yeah, yeah, I think that's enough for this week's session. I just summarized whatever was discussed in this week, excluding some of the topics that I felt were needed more time than that were allotted to them, and we didn't need to go into the details of those topics. So if you think that there was something, if you have any question, then you can ask me. If most probably I will get back to you on that in the next week, because I don't have much grip on this topic. But if I know that, we can clarify the doubts now itself. And moreover, if you have some doubts in the assignments, so I see that some people has have doubt in the why some questions were wrongly answered in the assignment. I can see that previously, that was the previous year that that was the case more, but this year most of the assignment answers are correct. So, but still, if there are some incorrect answers, we can discuss now itself, and I can convey or forward the message to the NPTEL team. So now the floor is up to you guys. You can ask question.
Okay. Hello.
Yeah, Prachi, do you have any question?
Yes. Actually, I just want to know whether the assignment score we can see now, or it will be after means all the assignment completed.
Assignment 4, I couldn't understand the
Esti-
question.
no. Assignment score. The mark means which is wrong and right. I think it is after some time the assignment solution also somewhere it is means
I think
declared.
I think you should be able to see the assignment answers.
Okay. Is it right? Okay, I have not searched that one. That's why
Oh,
uh, I
yeah. So
I
actually,
think there is a assignment score or something review assignment. There is one option. So I thought there it will be like how much you have scored. It's like that, but it's not there. Okay.
so let me show you. I will share my this screen.
Okay, if it is there, can you please see? So to see.
Yeah. So what I will do is I will share my screen. Oh,
Okay.
this is not good. So I as this NPTEL DA duty, I have to also register to this course which I am TA of. So as you can see, I can see the answer that I have given and the answer that is
Okay.
correct. So I don't think they will give you a like a cumulative score of all the assignments together as of now, but each assignment individually you can check.
Okay.
Okay.
Uh, is it like the lecture material and assignment? There itself the solution also there.
Yeah, yeah. See, the solutions, like the answers
Okay,
are.
once the due date is means assignment date is completed, after that we can get the solution
Exactly.
completely.
Yes. Yes.
Okay. Then thank you. I have not checked that.
Oh, okay.
Okay.
Hello, sir.
Yes.
I have one question: how to submit an assignments?
No, you just have to click on these things. See, you just have to click on these things, and they and as it is, you can. Okay, let's go to this week 6 and let's see the week 6. I don't think the I
Hmm.
don't think the answers of week 6 are shared yet. So you just select your answers, and when the due date passes, it or you can click on the submit answers. It will automatically submit it.
Yes.
Okay.
Okay, sir.
Okay.
Yeah, hello, sir.
Yeah.
I haven't. I haven't previous recorded lectures where it can be.
So okay. So if you see this, you'll be able to see this. So the main lectures will be here, and the problems, the other lectures that we are going through once a week, that will be stored in this problem solving session. So if you click here,
Mhm.
so if you go to the course page, the problem solving session, you will
Hmm.
get this link to a Google Sheet where you get all the links for the YouTube videos and the drive where I will share this the where we are working. No, we are working on the hands-on notes, so we'll share the notes also.